This lecture continues our investigation of magnetic force on wires, or basically the force on moving charges. So what we're going to cover in this PowerPoint set of slides is we're going to talk about the superposition of magnetic fields, the magnetic field from a wire, and what happens when I have two wires with current traveling on them and the wires are parallel. Okay, so in terms of the superposition of magnetic fields, whenever I have more than one object generating a magnetic field, the two magnetic fields will add together. Normally, this isn't a problem, but if you're doing an experiment, what happens a lot of times is you forget that there's another magnetic field that's already present, okay? And that's Earth's magnetic field. So if you're ever wondering, why some of your data looks off, if you forget Earth's magnetic field, that effectively becomes like a systematic error. You're missing an entire 50 microteslas, more or less, worth of magnetism. So the magnetic field from a wire has this formula that's for the strength, which is proportional to current and inversely proportional to distance to the wire. Okay, or B is equal to mu naught over 2 pi times the current I divided by the distance R. Okay, that's distance, not the radius of the wire or anything like that. Okay, so it's distance to the wire. For the direction, we have our right fist rule. The magnetic field is going to be going around the wire, and your thumb is going in the direction of the moving charges, moving positive charges or conventional current. So if I have two wires, okay, I'm going to have a magnetic field from both wires at the same time. Okay, one wire will generate a magnetic field and the other wire will experience a force because it's carrying a current in that magnetic field, and vice versa. Okay, so we're going to be using the right fist rule for both wires. Okay, be careful with this because a lot of times I see people using right hand, left hand and placing it down for the two wires and trying to imagine the fields. The problem is you have a left hand. Okay, it's the right fist rule for both wires. Okay, and usually what we'll do is we'll ask, what's the direction of the magnetic field at a certain point? So you draw the magnetic field, and at that point, one wire will be pointing one way, the other wire will be pointing some other way, and the combination of the two, okay, will just be a vector addition. Okay, at least graphically. We're probably not going to be working too much with the magnitude formula because the magnitude formula is not in the IV data book. So I don't really foresee them making you use it. However, you should be aware that as you get farther from the wire, you get weaker. As you get more current, you get stronger. Okay, so here I have two wires and the magnetic field from those two wires. Okay, so we need to look at what's going on. Okay, in this case, my current is for both wires is going into the page. Okay, so again, I would take my thumb and stick it into the page, at which point on my right hand, on my right hand, right wire, I'm going to the right, something like this. Okay, and so when I want to superimpose it, okay, right here in the middle, okay, the left one will be going and has a magnetic field downwards. On the right one, I'm going to have a magnetic field upwards. As long as we're talking the same distance, those two fields are going to cancel, and I'm basically going to end up with no magnetic field at all in the middle. Okay, at some other point up here, my magnetic field from the left is going like that. My magnetic field from the right, okay, a little bit weaker, but it'll be going like that. Okay, and the combination looks something like that. Okay, the net result of all of this, okay, is that my magnetic field from these two wires is going to look something like this. Okay, something like that. Okay, almost looks like a pair of eyes around right now. And this is a picture that we've seen before, okay, or something similar before. Okay, and where we've seen it before is in equipotential surfaces from two positive or two negative charges. Okay, and that brings up a good point because the electric field and the magnetic field are frequently perpendicular to each other. Okay, and so it should be no surprise that my magnetic field looks like the equipotentials because the equipotentials were also perpendicular to the electric field. Okay. So when I talk about the magnetic force on the wire, I can calculate the magnitude using the formula F is equal to the magnetic field B times the current I times the length of the wire in the field. That's what L is. Okay, so B, I, and L. Notice it's only the perpendicular component of B. Okay, or the other way I would write this is simply B, I, L times the sine of theta, where theta is the angle between the wire or the current, I should say, and the magnetic field B. Most of the time it's going to be perpendicular, but pay attention, okay, because those frequently fall under the trick questions. Okay, so if I have two parallel wires carrying a current, they both generate a magnetic field. The left wire generates a magnetic field, the right one experiences a force. The right one generates a magnetic field, the left one experiences a force. In fact, the net force the force on both of them create a Newton's third law pair. Okay, the force of wire 1 on wire 2 is going to be equal to the force of wire 2 on wire 1, but equal but opposite. Okay, when I do the full formula, okay, the force is going to be equal to the magnetic field, where, okay, this is my magnetic field, mu naught over 2 pi times the current on wire 1, divided by the distance between the two wires. That's what D is in this case. Okay, times the current in wire 2 and length 2. Okay, assuming the length of my wires are the same, then I'm going to end up with the same formula in the other direction. Okay, so rather than calculate the magnetic field and do right-hand rules and then right-fist rules, what we do for two parallel wires is we simplify it down a little bit into kind of a rule of thumb or a simple memorization. Okay, so in the case of two parallel wires, if the current on the two wires is going in the same direction, then the force on the wires is going to be attractive. Okay, just like when two people are attracted to each other, they walk in the same direction. Okay, if on the other hand, if the currents are going in opposite directions, let's say one is going up and the other one is going down, then the force on those two wires is going to be repulsive. They want to move away from each other. Okay, that's because they're moving in the opposite direction. Okay, and just to remind us, okay, the two forces making Newton's third law pair. Okay, so in terms of the magnetic field, when the two wires are moving the same, that's my, this is what my magnetic field looks like on the left. When they're moving in opposite directions, my magnetic field looks like the diagram on the right. Okay, and again, maybe you recognize some of these from those equipotential surfaces that we used to draw. Okay, so don't forget that there's that Newton's third law. Okay, we talk about fields, okay, electric field, gravitational field, and now magnetic field, but there's something generating that field. So the object generating that field is what will experience the third law pair. Okay, it may be very massive and experience very, nearly zero acceleration, but it still experiences that force. So just like in gravity, okay, if I jump up, yes, I am attracted back to the Earth, but the Earth is equally attracted to me. The difference is the Earth is many, many, many more times more massive, and so it really doesn't budge. Okay, however, in the case of magnetism, a lot of times we forget that there's something else generating that force. Okay, so at times you may have to recall that there's a third law pair in action. Okay, and we'll see that in some of the paper 2 style problems that we'll look at. Okay, so in this case, I have a particle, it's moving, in different directions. and we need to figure out what the force on that, or direction of the force on that particle is. Okay, so using the one on the bottom, it's moving to the left. My magnetic field is into the page. Okay, but what we don't know is what is the charge on this particle. Okay, let's assume it's an electron. In that case, it's moving to the left. My magnetic field is into the page, so my force is actually going to be up. Okay, if you did the right-hand rule and got down, that's actually correct. Okay, however, I said it was an electron, and so therefore I have to flip my directions. Okay, same thing for all of these. Okay, if I do the right-hand rule and flip them because it's an electron, the force on my charge is always going to be moving towards the middle of this picture. Okay, and that's going to be important because the force on a moving charge is always going to be perpendicular. Okay, that's what result of the right-hand rule and result of the cross product multiplication that we did for the two vectors. So what we're going to see in a number of problems as we move forward through this is that the force, as long as the only force I have is the magnetic force, then that's going to have a magnitude of Q times V times B. And we'll ignore the sine theta because of the perpendicular aspect. Okay, and the charged particle, as a result, okay, is going to end up moving in a circle. Okay, again, that the acceleration or the force is always towards the center, always perpendicular. So the charge will never accelerate. Okay, it will change direction. I shouldn't say accelerate. It will never increase in speed. So it's going to be uniform circular motion. And I'm going to set that QVB, magnetic force, equal to my centripetal force, okay, mv squared over r. And this is a key aspect because later as we go further into this unit, we're going to find that there's a piece of equipment that's called a mass spectrometer that basically is built on this concept. Okay, by using ions and sending them through a magnetic field, I can determine what the mass of that ion is, and given that mass, I can then tell you what element that ion is. Okay, so thank you.